And then another variation could be that you could be given an undirected graph instead of a directed graph. Let's say the graph is undirected. So let's say your task is to deliver mail to the inhabitants of a city, and you want to find a route whose starting and ending point are the post office, and that is basically a vertex with ID 1, and it needs to go through every street exactly once. So that means you want to construct an Eulerian cycle in this graph. And again, the burden of determining whether or not that cycle even exists is on you. So it's possible that there may not exist such a cycle. So that means this time you have to use the property for an undirected graph to make sure that uh, the graph is not in multiple pieces. That means at the end of the execution of your Herholzer's code, there should be no edges left in the adjacency list, otherwise it's impossible. And also the the subtlety behind an undirected graph is that when you use an edge, right, remember each edge is present in is present in two copies in the adjacency list, right? In the adjacency list for S, the neighbor U would appear somewhere, and in the adjacency list for U, the neighbor S would appear somewhere. So when I start from S and I use up this edge to U, I can of course pop U from the adjacency list for S, but I also need to pop S from the adjacency list for U. Otherwise, it's as if I am seeing this as a directed graph with these two edges, and that can be used two times. Right? Whereas in reality, it's an undirected edge that can be used only once. So this additional requirement to be able to delete S from the adjacency list of U and being able to do so in a fast way will make us think twice about using an adjacency list representation, because in a list representation, if I want to find and delete the occurrence of S in the adjacency list for U, I have to do a linear scan in the adjacency list for U, which I preferably don't want to do. So it's better for me to use an adjacency map in such a circumstance where checking for an edge and deleting it takes a constant amount of time. So that's the additional subtlety if you are given an undirected graph. So yeah, so with that, let me just see if there is anything else. No. So these are some things to keep in mind when if you get variations of this problem. Yeah, Abhinav.
Sorry, I forgot to lower my.
Yeah. Mehul.
Yeah, so the starting node is given to you in these problems?
Yes, in these problems the starting node is given. Although if it was an Eulerian cycle, it wouldn't matter. But yeah, so level 1 is where you start in the directed graph version, and the post office has an ID of 1 in the undirected version. So in both cases, you're doing depth first search starting from vertex 1.
Yeah, and so but in the teleporters in the teleporters one, you had where the solution was you had an array of 1 to n. Uh, how do you know what the last one is where you check the degree? If you look in the code for this, where was the code? The next slide, I think.
Mhm.
Yeah, so where you say if I equal to n and in degree not equal to out degree plus 1. So how do you know what is n until you can actually do the whole DFS, right?
No, n is just the so the vertices have IDs from 1 to n, right? And you're given that this is the 1 is the source and n is the destination.
Oh, okay. So okay,
So
if you're
yeah, so
given that.
basically this check is a check that for the destination, for the destination of the Eulerian path, the in degree must be one more than the out degree.
I see. So, and same with the mail problem.
Yeah. For the source, the out degree should be one more than the in degree, and for every other vertex, the in degree and the out degree need to be the same.
right. So for these problems, the destination is also given to us in the question in the interview.
Uh, well, that may not be given. Yeah, the
I see.
destination. Well,
I
so
think the first problem tonight did not. You need to figure out the destination, right? D. Whereas in the last two examples, the variations, the destination.
yeah, so I think it's not a coincidence that the destination was not given in the lead code problem, but you didn't have to do the check, right, to make sure that the path exists, that an Eulerian path even exists. If you have to make that additional check, then uh, giving the destination makes it a little easier to do the check, right? Otherwise, you have to check that there is
It's
exactly one vertex that has an in degree that is one more than the out degree, and that has to be your destination. So
so suppose it's a cycle, then this condition won't be true, right? In the cycle.
yeah, so if it's a cycle, then yes. So yeah, you have to look at both of those conditions. So that's why the code would become longer, and that's probably why they don't ask that even in these comparative programming sites.
And that's fine. If you find an
Yeah,
Euler's path in the first problem tonight, then it's implied that D will have that thing.
yeah, but yeah, well, yeah.
Because if you don't have a D, it's a cycle. Then I mean, if the S and D don't satisfy the property.
No, so the problem is with a directed graph, things can get more complicated where you can have multiple pieces and then you can have edges from one piece to another but not back. So it can become quite non-trivial to. I mean, it would still be linear time, but then you would have to do additional checks. When you construct the path, you need to make sure that uh, you uh, anyway. It's not relevant, I think.
Okay,
Uh,
all right,
but
okay, cool.
but Yeah, so there are a bunch of rules here. So in the worst case, you would have to like check for everything, right? You have to find whether the graph is Eulerian or not. You have to identify the destination if you want an Eulerian path, and uh, and then make sure that the graph is in one piece when you finally construct the path. Okay, any final questions before we stop? Okay, let me see the Q&A tab. Okay, Mumtaz.
Hi, Omkar. So my comment is actually not about this session. It's a general comment. So if you're done with other questions, can I ask that?
Yeah, sure.
So just like you told us at the beginning, right? Like if you have a problem where you see the traversal of all edges is required, you should think about Eulerian cycle or stuff like that, right? So is it possible to, I don't know, maybe it's wishful thinking to have one document or something where this kind of patterns can be identified for like all classes of problems, like trees and graphs? Yeah, I don't know. Maybe it's too wishful to.
I think we do need to come up with a document. So, uh, my what I am trying to focus on right now is to cover more topics. So it would obviously I have been single-handedly building this all out. So we do have a few more people now in the team. So uh, I think if you raise this with operations, we could they could prioritize it so that someone can take all these patterns, or maybe if some student among you, if you have already somebody who's gone through all of my videos which are based on patterns,
Sure.
and
Yeah. So, yeah. So the only thing is that I wished when I had gone through the foundation ones, I had made notes. It's just probably a matter of making notes, right? Because
yeah.
in the foundation video, you do try to identify patterns, but is it that someone needs to do that again, go through all those videos and try to come up with a document?
Yeah, well, in the foundation video, so that was also done under time pressure. So I was under, I had been given a deadline that I need to make those videos, one for each topic. I need to make the videos in 2 weeks, because I also had to teach the live, pick up teaching the live class. So it was very hard for me under those time constraints to, make notes as well as, uh, make the content. So I focused on the content itself, assuming that the notes can be made. Um, they don't have to be made by me. Anybody who sees my video might be able to.
Right. But as you can
Whether
well imagine, it would be something that's really valuable for all the IK students.
yeah. I think we will get to that. I just don't know when, because someone else will probably have to do it based on my videos.
Okay. Thank you.
Just to add
So
to that, on last
yeah,
class,
just one thing, 1 second, Mehul, because I just saw a question here by Jason. How does radix sort here give us linear time, not n log n, like other best case scenarios? So Jason, if you're still there, since our strings are of length 3, the idea is that we will do 3 counting sort passes, and each counting sort pass takes linear time, even in the worst case, because we have only 26 different buckets or uh, values possible at that, or at any position. So we just have to count how many copies of each letter are there in that position, and then we can easily create the sorted output in linear time, even in the worst case. And since we have only 3 iterations, this would be done in linear time overall. If you forget the details of counting sort or radix sort, you can look at the sorting foundation videos, and this is very clearly like a linear time algorithm in the worst case, given the constraints that the strings are of exactly length 3. Yeah, Mehul.
yeah, no, this is great teaching. I just wanted to about the previous person's thing, right? Last class also I had mentioned about the uh, cheat
Cheat
sheet,
sheet. Yeah.
right? And so what I would suggest is, we have to give our interviews soon in the next few weeks.
Mm.
And because our class started in September, and so we've been trying to work with them since then. If you can just give, if you somebody you can just start with like even 50% of the patterns, or even 30% of the patterns is better than not having anything. And so if you guys can just have a work in progress, this pattern sheet with some examples and some lead code problem numbers. Hey, this is this pattern, that is that pattern. And so, and then you can keep making it better over time. But if you spend another 2-3 months giving us a very nice sheet, then we don't have anything in between. So if you could, and
Okay.
one of us can start, but at least have something in the next few weeks would be great.
Okay. So basically, you want I do have a sheet with all the problems that I have covered. I think there are about 220 or so of them, with broad names for patterns, not specific names, but things like bottom up DFS, or boundary walk DFS, or binary search for optimization, bisection search, things like that. If you I don't have the pattern itself in that sheet, but I have the name. Is that good enough for now?
Yeah, we can put a Google Doc, and then you can make it better in the next few weeks. Just take a few important things you are seeing being asked, and just expand on some of the things you start, and then you can delegate it to some other guys in your team to add more. So I
Yeah.
think that's good. That's a good start.
Okay.
Thanks.
Yeah, I was just assuming so far that the PDFs of my live classes, somebody could take a if the PDFs are not directly useful, somebody could easily take a screenshot of the relevant patterns and put them in a doc. Uh, uh, I'm not sure. I think there should be some students who've done that. So in case any of you has already done something like that, just ping me. Yeah, Paul.
Yeah, Omkar, I have something uh, around those lines, but
Oh, okay. Yeah,
I can get it reviewed by you, and then
sure. Okay, that would be good.
thank
Omkar, can you please move to the screenshot for this post office problem, the solution? There was a code, I guess.
Uh, Post office. Oh, you mean mail delivery? Okay.
Yeah, mail delivery.
Yeah. So I have two different uh, pieces of code here. Um, yeah, I don't want to confuse you, but the degree check is actually not separately required. So here I have the degree check, and on the other side, in the other implementation, I I just removed it because it's actually not required because uh, as long as the graph is in one piece, as long as the graph is in one piece, this is an undirected graph. Remember, um, so you do need to check that it's in one piece. That check is required. But if you don't, even if you don't check for the degrees, if you just run the algorithm, here Holzer's algorithm, the iterative improvement algorithm, and whatever you build, whatever the algorithm outputs, if you treat that as the Eulerian path and then you check to make sure that there are no remaining edges, that would be sufficient. You don't this becomes redundant essentially. But I'm still keeping it here because it's actually required for directed graphs. You can't remove this check from directed graphs because there can be edge cases like this in a directed graph. So let's say this is the source, this is the destination. Um, let's say I don't do a degree check on a directed graph. I just check whether I covered all the edges by the end. So I start from S. My algorithm would go here to U. It would do the end up building SUD. Then it would backtrack to U. It would backtrack to S, and it would uh, come to V and then come to D. And now these two paths would the second path is not even a cycle, so it would get and it's also not a disconnected piece, so it would get blended in with the first path in some weird way, which is not what we want. So that degree check handles such test cases in directed graphs. So there's no harm in just always doing it rather than remembering so many specific things. Just do the degree check for both undirected and directed graphs.
And you have a for loop to ensure that all the edge list is covered, right?
Hmm.
I was just thinking if we could plainly check whether the size of that R stack where we are appending the nodes, if that is not equal to the n number of vertices, wouldn't that mean that the Eulerian path does not exist? Or am I missing? Am I confusing with Hamiltonian thing?
Yeah, if you know the number of edges, which you do in this case, it's m. Yeah, so the number of the size of the R stack or the result should be m plus 1, right? Since it's a sequence of vertices, so it's m plus 1, so even that might work.
Okay, that would eliminate that for loop, right? Where we have this print impossible thing.
That would eliminate the for loop. I haven't tried that, but I'm guessing that would work.
Okay, the size of R stack should be m is m plus 1, not n, right? N is number of vertices. I should not equate
Yeah,
the
yeah,
size of R stack. Okay,
yeah, m plus 1 because An Eulerian path would have exactly m edges. Uh, each edge is used once, and since we start from the source of the first edge and end at the destination of the last edge, we have m plus 1 vertices in the sequence.
And also in this undirected graph, you are deleting both the nodes, right?
Hmm.
Both the node to neighbor, neighbor to node.
Yeah.
Why don't we just while we build the adjacent list? Why don't we just do one of it? Would that work so that we don't delete two?
No, because you don't know which you. If you do only one, you'll be putting that in only one direction, and you won't find it in the other edges. You don't know from which direction you will want to use that adjacent that undirected edge.
The same argument holds true in the for loop as well, right? And say the DFS code. You don't know which of those directions you're going to hit first. Okay, whichever is hitting first, you are removing the other one as well.
Yeah, that's fine. But if you're starting from some vertex and you need to traverse that edge in that particular direction, um, uh, there may not be a way out. I mean, just to give a simple example, if you have source S and you have, let's say, a graph, an undirected graph like this, right? Let's say U, V, and W, and for whatever reason, I just add this copy of the edge from U to S. I don't add it from S to U. Then when I start from S, I'm stuck here. So I have to add
Um,
both because I don't know from what direction I will want to use it. Right? I
I
need
see.
it to
Okay.
be like this. I need it to be like this so that when I am at S, I can I can visit the edge in this direction. And if I'm at U and I was coming from that side, I can use the edge in the other direction. I can't just have one. That would make it a directed graph.
I see. Okay. All right. I need to think about this. I'll look at the solution. I'll think about it.
Sure. Okay, let's stop then. And thank you all.